In Lab 1, we are observing the motion of an object moving at constant velocity and constructing a computational model of the object's motion. Setting the experimental data in comparison to predicted data will be important in understanding the motion of objects under optimal conditions in comparison to real conditions. An object moving at constant velocity indicates that the object is moving at a constant speed in the same direction. Newton's second law, which states that the acceleration of an object is dependent on the net force acting on an object and an object's mass, can be applied to explain an object's motion. In addition, the ratio of change in velocity to the change in time, acceleration, is equal to the total of the pushes and pulls acting on an object, or the net force on an object, divided by a mass. Therefore, for an object to have constant velocity, the net force on the object must be equal to 0. In this lab, I chose to analyze a video of a tennis ball rolling across a flat table. I will be analyzing the video from frames 107 to 136 because the ball is still accelerating in the beginning of the video and leaves the video frame at the end of the video. The video camera used to record this motion did so at 30 frames per second, which is indicated in the tracker. The calibration stick is set to the diameter of the ball, which is 0.0654 meters. The origin is set at the center of the ball in the starting frame, with the positive x-axis pointing to the right. Since the ball is traveling to the right during the video, it is traveling in the positive x direction. However, I could have also picked alternate orientations for my axes. For example, if I chose right of the origin to be the negative x-axis, the ball would be traveling the same speed, just in the negative x direction. Thus, the ball's position vector would only be changing in the negative direction, and the position versus time graph with the new orientation would have a negative slope. From Tracker, I obtained the observation start time, time of the last observation, and the ball's initial position vector. I then calculated the ball's initial velocity vector using the first two position data points and the corresponding time data points. This corresponded to 1.10900 meters per second. Using the data from the experiment, I created a computational model of the ball's motion in GlowScript. In line 31, I input the ball's mass, which is 0.0577 kilograms. Line 34 indicates the ball's initial position vector, which was 000 meter. Line 35 indicates the ball's initial velocity vector that we calculated earlier, 1.10900 meters per second. Line 38 indicates the beginning of our observation time, and in line 39, I changed the model time step increment to be the same as the observational time step from Tracker, which is 0.033 seconds. Line 48 indicates that we are going to create a model from 0 seconds to the last observation time at 0.933 seconds. And since we want to create a model in which the ball has constant velocity, the net force vector is set to 000 newtons in line 53. Line 57 has modified the display to Newton's second law. Since the net force vector is set to 000 newtons, the mass of the ball is negligible and the final velocity is equivalent to the initial velocity, meaning the velocity is constant. Line 59 has also been modified to display the position update formula. The code generates this model and graph of the ball traveling at constant velocity. This graph compares the ball's experimental position to the computational model's predicted position. Velocity is defined as the rate of change of displacement with respect to time. Therefore, the velocity of an object is equivalent to the slope of a graph comparing displacement versus time. In the graph, the blue line represents the predicted position of the ball from the computational model. The linear slope indicates that the ball's velocity is constant, and therefore the net forces acting on the ball are equal to 0. In comparison, the orange line represents the experimental position of the ball actually taken from Tracker. Since the data points are not perfectly linear, it can be concluded that the velocity is not constant during observation. The discrepancy between the model and the experiment can be attributed to the non-zero net force acting upon the ball during the observation. This diagram illustrates some of the forces acting on the ball during the time of observation in the experiment. In the y direction, the ball is acted upon by the force of gravity in the negative y direction, and the normal force of the table pushing back up against the ball in the positive y direction. Since these forces are equal to each other in magnitude, but opposite in direction, the net force is equal to 0 in the y direction. Since there is no initial velocity or acceleration in the y direction, the position of the ball in the y direction never changes. In the x direction, there was the initial push to set the ball in motion, but that force has already been taken into account. In the negative x direction, however, the force of friction is acting on the ball, causing the ball to slow down by opposing its motion. Other forces, such as air resistance, could also have impacted the ball's motion. To improve prediction in the future, the experiment could be conducted again on a smoother surface with less friction to decrease the net forces acting upon the ball. In conclusion, an object at constant velocity experiences no acceleration, since the net forces acting upon the object equal to zero. The computational model illustrates the ball's motion under ideal conditions of no net forces. The experimental data, however, deviates from this. And this deviation from the computational model indicates that there are non-zero net forces acting upon the ball in the real world. And some examples of these forces would be friction.